Alright, let's talk about triangular square root matrices. A triangular matrix is a matrix with zeros in the upper or lower triangular portion of the matrix. So as an example, we can have a matrix U, meaning upper, and it can have the values 4, 2, 3, 2, 0, 6, 1, 5, 0, 0, 5, 2, 0, 0, 0, 3. So you notice on the upper triangular portion of this matrix are values, on the lower triangular portion are zeros. So a lower triangular matrix would look like this. Just as an example, you have 8, 0, 0, 0, 1, 11, 0, 0, 4, 7, 9, 0, 3, 8, 2, 4. And this is just an arbitrary example. It's useful in many statistical methods to find the triangular square root of a symmetric matrix, and we use the Cholesky method in order to do this. Now suppose we want to find a triangular root of the square matrix A, and A will have the values 4, 6, 2, 6, 16, 3, and 2, 3, 9. Notice this is a symmetric matrix, and we'll be using this one today. We can describe each element using its row and column location. For example, A1, 3 would be the element in the A matrix in the first row and the third column. So A1, 3 would be 2. And let's say A2, 2 would be the second row, second column, and the value there, which is, right, that's 16. So to find the first diagonal element in the triangular root matrix T, we use this formula. We use T subscript 1, 1 is equal to the square root of A subscript 1, 1. Once again, that is to find the first diagonal element in the triangular root matrix that we will get, and we will call that T. Now I'm going to do this on this sticky note here. So T is going to be a 3 by 3 matrix, and the first element here, these are going to be the elements, the values. So the first one is T11, which we're going to do here, which is the square root of A11, which is 4. So the square root of 4 is 2, so that will go right there. This is easy, but it gets a little harder. The remaining elements in the first row of T are found by dividing the corresponding elements in A by T11. So let me demonstrate that here. I'm going to move this over. Let's stick it over here. So T12 is going to equal A12 divided by T11. You should remember that formula. So A12 is 6 divided by the first element in the first row and the first column of T, which we just found to be 2. So 6 divided by 2 is 3. So we can now put 3 here. And then to finish off that first row, T subscript 1, 3. So the first row, third column is going to be the first row, third column of A, which we found up here to be 2, over T subscript 1, 1. So 2 divided by 2 will give us 1. So is that pretty easy? Yeah, well, it gets a little harder now. The remaining diagonal elements, so we have T22 and T33, are found using this formula. We have Tii equals the square root of A subscript II minus the summation as k goes from 1 to I minus 1, summation of T squared, and that's T subscript Ki. So the T diagonal elements after the first one, so that would be once again T22 and 33, are found by taking the square root of a quantity. This is the quantity. The quantity is the corresponding element in A. So we're going to do 22 and 33, so this would be 16 and 9. Adjusted by subtracting from it the sums of squares of all the elements in T that are above the location of the new desired element. So what am I talking about? It always helps if we do an example. So T subscript 22, so that's the second row, second column, this one here, will be equal to A2 minus, we know I is equal to 2, so I minus 1 will be 1. This k goes from 1 to 1. Summation of T sub k, our I is 2, and this is squared. So we're just plugging in numbers right there. So what is this equal to? So it's equal to the square root of, what's the second row, second column element in A? It's 16 minus, so k is just going to be 1, so we do T sub 1, 2 squared. Well, we already found that up here. So this is going to be 3 squared. So 16 minus 9 will give us 7. So our answer that will go in here is square root of 7. Okay, so I want to go back. How did we know this? Especially this one right here. What is it? Well, we did it above. Let's just plug it in here once again. So the summation of T subscript K2 squared as k goes from 1 to 1 equals, so that's T sub 1, 2 squared, which is just, since k goes from 1 to 1, is T 1, 2 squared, which we found up here is just 3 squared, which equals 9. Alright, any questions on that? If you do, just pause the video and go back. But once again, we're just plugging in, this is the formula, okay? We're just plugging in numbers. You just plug and chug, and this is what you find. Well, if you think that's hard, it actually gets a little bit harder. The remaining entries in the second row, so for this example, it's just this one that's left, so T 2, 3. So the remaining entries in the second row are found by using this formula. The formula is T sub ij equals a sub ij minus, we have another summation here, summation of t sub ki times t sub kj, as k goes from 1 to I minus 1. Let me separate that here. And this is over t sub I. That's an eyesore. It hurts to look at, doesn't it? So, let me try to explain this in words, and then we'll do an example. So each remaining entry in the row to the right of the diagonal, okay, so just this one for now, is found by taking the corresponding element in A, subtracting a quantity from it, which is this quantity, and then dividing the result by the just computed diagonal element for that row. The quantity subtracted is just the sum of the products. So this quantity subtracted is just the sum of the products of the T matrix elements above the desired new element multiplied by the corresponding T matrix elements above the diagonal element. All right, what did I just say? Let's do an example. So we have T, we need to get this one, so T sub 2, 3 is going to equal, let's just plug in values. So this is our formula. So we have A sub 2, 3 minus, we've got summation of T sub k, what's I? I is 2 times T sub k, j is 3. That is, as k goes from 1 to I minus 1, what is I? I is 2, so k goes from 1 to 1. And that is all over T sub 2, 2. Okay, so we're just plugging in numbers for this element that we need to find. So let's plug and chug. A sub 2, 3. We look up here at A, we find that is 3. So it's going to be 3 minus, we know this is going to be T sub, since k goes from 1 to 1, so T sub 1, 2 times T sub 1, 3. So T 1, 2 we found up here to be 3 times T sub 1, 3, which we found up here to be 1. And because since k goes from 1 to 1, there's really no summation that we need to do. It's just as simple as that. Divided by T sub 2, 2, which we found to be square root of 7. So 3 minus 3 times 1 is 0 over square root of 7, so this value is going to equal 0. So let me go back to the mouthful of words that I said before and try to make a little bit more sense of this. So once again, each remaining entry in the row to the right of the diagonal, so this entry, is found by taking the corresponding element in A. So where is this element in A? It's this one, 3. So we're taking this 3, okay, and we're going to subtract a quantity from it, which we'll talk about in a second, and divide it by the result of the just computed diagonal element for that row. Well, for this row, we just computed this diagonal element, square root of 7. So we divide it, we do this element in A minus a quantity divided by the just computed diagonal element for that row, which was the square root of 7. So the quantity that we subtracted is just the sum of the products of the T matrix elements above the desired new element. Okay, let's stop there. The desired new element was this one. So the T matrix element above this one is 1. So we have 1. and that's multiplied by the corresponding T matrix element above the diagonal element. Well, that diagonal element was square root of 7, and just above that is 3. So we're going to take 3 times 1. Okay, and that's how we get this. Now, if you had a larger matrix, it'd be a little bit different. You would actually need to add elements. If this went out a little further, and there's a row above this, we take these elements, multiply them, and then do a summation. So we take these elements, multiply them together, and then the row above that, multiply them together and add those two rows together. But that's for a larger matrix. Fortunately, we don't have to do that this time. So now we can find this last one. We use the formula that we have right here. So it's going to be T sub 3 equals the square root. Let me divide that here. Of A sub 3, once again I'm using this formula, minus we have a summation T sub K3, and that's squared as K goes from 1 to, this time I is 3, so I minus 1 will be 2. So let's plug and chug. So we get the square root of what's the value for this one? It's 9. 9 minus, this time we do have a summation. So we have T sub 1 squared, which we found up here. So it's going to be 1 squared plus T sub 2 which we found right here to be 0, and that's squared. And since K only goes to 2, we stop there. To simplify, square root of 9 minus 1 equals the square root of 8, and that is our value that goes in here. Alright, we have our upper triangular root matrix, and we know that these values are going to be 0 since it's a triangular matrix. Alright, so how do we know that what we got was correct? Well, you can check this triangular square root matrix by pre-multiplying it by its transpose. So let's do that down here. So we have, I'm going to pre-multiply by the transpose. So we're going to get this here. Let me scoot that up. So we're going to have 2, 3, 1 going down, 0, square root of 7, 0, 0, 0, 8, times 2, 3, 1, 0, square root of 7, 0. This is going across, and 0, 0, square root of 8. And we multiply that out, what we get is 4, 6, 2, 6, 16, 3, 2, 3, 9. Look familiar? Yes, that's A. So that is going to equal A. And that's how you know that you did your triangular matrix correctly. Now notice we pre-multiplied by T and not post-multiplied. The order of multiplication actually matters. When we do matrix T times its transpose, so post-multiplied by the transpose, we get a different value that is not equal to A. And I'll show you that using Excel. Okay, here's Excel. I put in our A matrix, which we had at the beginning. And just as reference, I put the elements of A up there. So A sub 1, 1 would be 4, A sub 1, 2, 6, A sub 1, 3, 2, and so on. And I also did that for T over here. T sub 1, 1, 2, 2, 3, 3. Okay. Also, what I did is I inserted the formulas that we talked about in order to get these. We know that the bottom triangle will have zeros in the values. And as we talked about before, to get T sub 1, 1, we take the square root of A sub 1, 1, so the square root of 4. So let's do that here. Square root of, this is A sub 1, 1. I'm sorry, gotta do equal sign. And that will, of course, give us 2. Now for T sub 1, 2, we have that is equal to A12, which is 6, divided by what we just found, T11, which is 2. And our value is 3. For T sub 13, first row, third column, we get A13 divided by T11, which is 1. Now we know that these values are 0 down here. So let's get the second diagonal, T sub 2, 2. It gets a little more complicated. So this is equal to the square root of A sub 2, 2, which is 16, minus, it's a summation, T sub 1, 2, which is this 3 here, and that's squared. And what we get is this value. I brought it over here. If you look at the top, this is actually the value of the square root of 7, just in as a decimal point. Okay. Now for T sub 2, 3, as I indicated up here, it's going to be A 2, 3, which is 3, minus a summation of T sub 1, 2, which is 3, times T sub 1, 3, which is 1. And I'm just following the formula that I have above this, divided by T sub 2, 2, which is the square root of 7. And we get 0. And for the last one, T sub 3, 3, this is the most complicated. It is the square root of A sub 3, 3, which is 9, minus a summation. And what's the summation? It's T sub 1, 3, which is 1, plus T sub 2, 3, which is 0. The values above it. We're going to square those. And we get that, which I did over here. If you look at the top, it is the square root of 8 in decimal formation. So that is equal to what we got before with T. So let's take the transpose of that. So I'm going to do the transpose function. Sorry. Of this matrix. Control Shift Return. Okay, now let's do some matrix multiplication to demonstrate what we talked about before in order to check our answer. When we pre-multiply by the transpose, we should get A, which we do, which is right over here, and they're equal. Now, what does it look like when you post-multiply by the transpose? T comma T transpose. It's totally different. So once again, in order to check your triangular matrix, you're going to pre-multiply it by its transpose, and you should wind up with the original matrix A that we got here. And that is how you do the triangular square root matrix. Once again, it's using the Cholesky method. I hope this was fun and entertaining for you. Have a good day.